Hello and welcome to another geometry lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 5, Lesson 9 on rotations in the coordinate plane. We've seen all of our real tools that we're going to be using in the coordinate plane, like the distance formula, the slope formula, and the midpoint formula. We're now going to go back and revisit some of the rigid motions that we saw in Unit 2, but exclusively in the coordinate plane, and we're going to start today with rotations. So let's get right into it. All right, and let me basically repeat what we just talked about. So rotations in the coordinate plane. Now that we have the tools of coordinate geometry, those three major formulas, we will look at the three major rigid motions. Those are rotations, line reflections, and translations, but in the coordinate plane only. We begin in this lesson with rotations. So let's look at exercise number 1. In the diagram below, segment AB is shown with endpoints at A, 1, 5, and B, 7, -3. Letter A. Draw segment A', B', the image of segment AB, after a counterclockwise rotation of 90 degrees about the origin. Show the mapping below. All right, well remember, I have a very sophisticated way of doing rotations by 90 degrees, whether they're clockwise or counterclockwise, doesn't really matter. In this case, it's counterclockwise. So this is how I always suggest that you do it. You take your piece of paper and you rotate it 90 degrees counterclockwise, right? And when you do that, you can now say, well, A, which was at 1, 5, will get mapped to A', which is now at -5, 1. And B, which is at 7, -3, will get mapped to B', which is at 3, 7. And once you do that, you then move your piece of paper back and you plot. So A' is at -5, 1, A', and B' is at 3, 7. And then I'm just going to kind of hand sketch this in. Should have had my ruler, but somehow I don't. Anyway, there it is. Simple enough. Okay? Let's take a look at letter B. Find the lengths of AB and segment A', B' using the distance formula. Show your calculations. All right, well, let's do the distance formula for segment AB, and then I'll have you do the distance formula for segment A', B' on your own. All right, so the length of AB. I'm just going to start by saying AB equals, and I'll have the square root, right, of 7 minus 1 squared plus -3 minus 5 squared. All right, 7 minus 1 is 6 squared. -3 minus 5 is -8 squared. 6 squared is 36. -8 squared is 64. That gives me the square root of 100, which is 10. All right, so the length of AB is 10. Why don't you go ahead and use the distance formula to find the length of A', B'. Pause the video now. All right, here we go. So I'll label this as A', B' equals square root. Again, x2 minus x1 is going to be 3 minus -5 squared. y2 minus y1, 7 minus 1 squared. A', B' equals 3 minus -5 is 8 squared. 7 minus 1 is 6 squared. A', B' equals 64 plus 36, the square root of that, which is the square root of 100, which is also 10. My, oh my. Shocking, right? Actually, not so shocking. Letter C. What is true about the lengths of segment AB and segment A', B'? Explain why this would always be true for a rotation. Well, what is very obvious is that their lengths are the same. And why is it always true for any rotation? It's because all rotations are rigid motions, and rigid motions preserve distance. All right? So they are equal. That answers the first question. Rotations are rigid motions, and all rigid motions preserve distances. The distances between two pre-image points will always be equal to the distance between the two image points of any rigid motion, regardless of whether it's a rotation, a line reflection, or a translation. All right, let's keep playing around with rotations in the coordinate plane. Now, because of the limitations of the coordinate grid, we will only rotate points by integer multiples of 90. So 90, 180, 270 in either direction. We can turn clockwise or counterclockwise. So let's take a look at exercise number 2. For segment CD shown with endpoints at C, -3, 8, and D, 9, 2, do the following. Letter A. Find the image of segment CD after a rotation by 180 degrees about the origin. Show the mapping below. All right, now 180-degree rotations will almost never be specified with a direction because, as we've discussed earlier in this course, it doesn't matter whether you go clockwise or counterclockwise. A 180-degree rotation is a half of a complete rotation, so it doesn't matter which direction you go. Now, if I wanted to do this with the method I looked at before, I could do 90 degrees clockwise plus another 90 degrees clockwise, and I will end up having that 180-degree rotation. So my mapping, right, C, which is started at -3, 8, will now be at C prime, and that will be at 3, -8. Likewise, D, which is at 9, 2, will end up being at D prime, which is at -9, -2. Now, I can rotate it back and plot my points. 3, -8, and -9, -2. And again, I'm going to just sketch my line segment in. And there's my line segment C prime, D prime. Awesome. Letter B. Find the slope of both segment CD and segment C prime, D prime in simplest form. All right, great. So now I just want you to do the slope formulas on both of these. Why don't you pause the video and go ahead and do your slopes. All right, well, slope is change in y over change in x, and it doesn't matter which sort of order we do them in. Let's do CD first. I'm going to do 2 minus 8. That should be a minus. Divided by 9 minus -3. All right, that's going to be -6 in the numerator and positive 12 in the denominator. And that's going to reduce to a slope of -1/2. The slope of C prime, D prime is going to be -2 minus -8 in the numerator, and -9 minus 3 in the denominator. -2 minus -8 is positive 6, and -9 minus 3 is -12. A positive divided by a negative is always a negative, and again reduces down to -1/2. Hey, look, these two line segments have the same slope. Cool. Take a look at letter C. Besides being the same length, see exercise number 1, what is also true about segment CD and segment C prime, D prime? Well, why don't you go ahead and write something down based on these two slopes? Well, they're parallel, right? They are parallel. Parallel due to the same slopes. Now, this is a fact that we haven't seen quite as much in this class, but we did see earlier in this course, which was that 180-degree rotations, and these are very specific to 180-degree rotations, also known as point reflections. 180-degree rotations of a line or line segment will always produce another line or line segment that is parallel to the pre-image. This is, of course, assuming that the point of rotation doesn't lie on the line itself, all right? So in this case, right, when we rotate CD by 180 degrees about the origin to get C prime D prime, we get an image segment that is parallel to the pre-image segment. And that will always occur with 180-degree rotations where the center of rotation is not on the line you're rotating. Now let's talk about rotation mapping rules. Sometimes, unfortunately in my opinion, we will be asked to determine the mapping rule or function for a given rotation about the origin. All right? So let's take a look at how we can think about those rules or how we can maybe deduce them by looking at a particular example. Exercise number 3. The point 7, 3 is shown plotted below. Determine its image after each of the following rotations and then state a general mapping rule for the rotation. All right, in other words, I want to take my point here at 7, 3. I want to rotate it counterclockwise by 90 degrees and get an answer here, and then I want to generalize. Let's do this one together, right? So if I take this and I rotate it counterclockwise about the origin by 90 degrees, all right, I end up seeing that 7, 3 ends up mapping to -3, 7. All right? I don't need to particularly plot it. I don't want to do that. I just want to know where it ended up going, right? Now, what would be the generalized rule? Well, it looks like the x and the y coordinates switched their locations, right? The 7 went over to the y and the 3 went over to the x, and then that old y coordinate got negated. So it appears now that the rule for rotating by 90 degrees counterclockwise, the x takes the place of the y, and then -y takes the place of x. So x, y gets mapped to -y, x. What I'd like you to do now is experiment in B and C with a 90 degrees clockwise rotation and a 180-degree rotation, which is also known as a point reflection, both about the origin. See where 7, 3 gets mapped to, and then see if you can come up with the generalized rule. Pause the video now and go ahead and try that. All right, well, let's do it first with this clockwise. I'm going to go, whoops, that didn't work. I'm going to go with a clockwise rotation. All right, so 7, 3 now becomes 3, 7. Oops, sorry, 3, -7. That makes a big difference. All right, so what happened there? Well, it looks like the old y became the new x, and when I negate the old x, it becomes the new y. So x, y maps to y, -x. Now let's go with our 180-degree rotation, also known as a point reflection about the origin. Here I can either do 2 rotations by 90 clockwise or counterclockwise, doesn't matter. But here we go, all of a sudden 7, -3 becomes -7, -3. And this is probably the easiest of them all. X, y just becomes -x, -y. In other words, right, all we do to do a point reflection through the origin, in other words, a 180-degree rotation about the origin, is we simply change the sign of both of our coordinates. We don't flip them at all, we just change their sign. All right. Now we have one last thing with rotations in the coordinate plane that is the most challenging thing that students do. When we rotate with centers other than the origin. Now this won't happen a lot, but sometimes we will want to rotate about a point other than the origin. This is more challenging, but it can always be done by keeping track of the image point's relative position compared to the center of rotation. And I'll explain exactly what I mean as we look at exercise number 4. Let's take a look at this one. On the grid below, triangle ABC is plotted along with point D. Letter A, plot the image of triangle ABC after a counterclockwise rotation about point D from 90 degrees, by 90 degrees, sorry. Label your image A', B', C', show the mapping below. All right, so this is going to be a little bit harder, especially for me. For you, it may actually be a little bit easier, okay? But let's take a look. Now, notice I'm rotating it counterclockwise by 90 degrees. So what I'm still going to do, just like before, is I'm going to take my piece of paper and I'm still going to rotate it 90 degrees counterclockwise. All right. Now, I want to think about where A's image point is compared to D, right? Right now, A's image point is going to be directly below D, and it's going to be literally 1, 2, 3, 4, 5, 6, 7. 7 units below D. So A prime is 7 units below D, right? So I rotate back, and where would 7 units below D be? 1, 2, 3, 4, 5, 6, 7. It's going to be at the point 4, comma, negative 4. So A prime is going to be at 4, comma, negative 4. Now I actually have to erase A prime simply because when I rotate my paper again, that point is just going to hang out there in space, okay? So I'm just going to get rid of it, but right when I rotated it, in fact, this might actually be helpful. Right, when I rotated it, yeah, that wasn't very helpful. But anyway, when I rotated it, A ended up being 7 units below D, and therefore I simply rotate it back and plot A there. Now that was the easiest one, okay? Now let's take a look at where B goes. So again, I'm going to rotate 90 degrees, okay? And now what I see is that the image point of B will be 1, 2, 3, 4, 5, 5 to the right, and 1, 2, 3, 4, 5 down. So B prime is 5 right and 5 down. Okay, so, and again, I'm just keeping track of where it is compared to my center of rotation instead of compared to the origin. Right? So it's nice when it's compared to the origin because then literally this would be the coordinate 5, comma, negative 5. But this is really 5, comma, negative 5 compared to where D is. So then I move it back like this, and then I got to get rid of this stuff. Oh, nope. I'll actually maybe move this down here so I can erase this and then move it back up. Hey! All right, so if I go 5 to the right, 1, 2, 3, 4, 5, and 5 down, 1, 2, 3, 4, 5, I'm at 9, comma, negative 2. All right, great, right? I'm at 9, comma, negative 2. I got to do it one more time. All right, hopefully, ooh, yay, I can do that. All right, so one more time. Now I care about where C is. Where is C? That is 1, 2, 3, 4 to the right, and 1, 2, 3 up. So C prime is 4 right, and 3 up. Again, rotate back this way. Whoops, rotate back that way. Erase. If I now go 4 to the right, 1, 2, 3, 4, and up 3, 1, 2, 3. 1, 2, 3, 4, 1, 2, 3. That went too far. 1, 2, 3, 4, 1, 2, 3. I will be at 8, comma, 6. I can actually leave that here this time. All right, and plot all the rest of them. A prime is at 4, comma, negative 4. And B prime is at 9, comma, negative 2. And I now have that triangle. And this is, of course, much more difficult than rotating about the origin, because when we rotate about the origin, we're just going to rotate our paper and literally read off the coordinates of our image points. Now what we're doing is we're really looking at where our image points are compared to the center of rotation. Let's answer the last piece of this problem. This one should be simple. Letter B, why must triangle A prime, B prime, C prime be congruent to triangle ABC? This should be old hat at this point because rotations are rigid motions. That's it, right? Anytime you've done a transformation and you're asked about whether or not it's congruent to the pre-image. The question is, was the transformation you did a rigid motion or not? If it was either a rotation, a line reflection, a point reflection, or a translation, the answer is yes, they're congruent, right? So why must triangle A prime B prime C prime be congruent to triangle ABC? Because rotations are rigid motions. I mean, think about it for a moment. If they weren't, right, and you took a picture of an image on your camera, or on your phone, and then you had that rotate 90 degrees, and all of a sudden distances and things got all sorts of funky, you'd be like, man, that completely changed the way that my picture looked, and all I wanted it to do was go from here to here, right? Rotations, translations, reflections shouldn't change the shape or the size of the figure, of the image. All right, let's do one more problem and then wrap this lesson up. Nice little multiple choice problem, exercise number 5. If the point A, -3, 7, was rotated 180 degrees about B, which is at 2, -4, at which of the following points would its image lie? All right, well, I'd like you to pause the video right now, play around with this problem, see if you can figure out where the image of point A would end up lying. All right, let's experiment a little bit with this. Point A is at -3, 7, right, which is right here. All right, the center of rotation is at 2, -4. That's B. Right? Ooh boy, right? So now I want to rotate this point by 180 degrees about this point, right? So literally, if I want to think about that, I want to take this thing and rotate it by 180 degrees. Now this problem would be much harder if we had something like, let's say, a 90-degree rotation. But the cool thing about a 180-degree rotation is that the point, the center of rotation, and the image point are all collinear, right? They're all collinear. So if I just think about this for a second, right? To go from A to B, right, I would have to go 5 units to the right, and I would have to go, what? That's 2, 7, 11 units down. Right? If I was translating, let's say, A to B, I'd go 5 to the right and 11 down. So its image point has to be 5 to the right and 11 down again. So if I simply take B, right, and B's coordinates, and I add 5 to the X, and I subtract 11 from the Y, I will now find the coordinates of the image point. All right, and again, that very specific one comes from the fact that it's a 180-degree rotation, and therefore the point, the center of rotation, and the image point are all collinear, so you can really think of, well, if I went from this point and slid it down to this point, and then I slid it in exactly the same direction and exactly the same distance, where would I end up landing? All right, so a very specific example there. All right, let's wrap this up. So in today's lesson, what we did wasn't all that different than the rotation work that we did back in Unit 2. Except here, we looked at it exclusively in the coordinate plane, and we got to verify some things that we already knew, which was that rotations preserved lengths. We were able to see that using the distance formula. We also saw that 180-degree rotations produced images that were parallel to their pre-images, and our slope formula helped us to verify that. All right. We also looked at the dicey kind of issue of rotating points around points other than the origin. And thankfully, that's more of a topic for more advanced geometry, although you could see easy examples of that on a state exam or a local exam or whatever. We will be doing more rotations in the coordinate plane as this course progresses. For now, I just want to thank you for joining me for another geometry lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.